Thank you so much for coming. I wasn't sure how many people we were going to get today because it's quite a niche topic, I think. And for those who've been in the FPGA world for a long time, it's difficult to leave. It's like a weird gravity well you disappear into. And I'm already seeing some old faces I haven't seen for a long time of people still in the industry, and people just don't seem to leave. So hopefully we can give some of that enthusiasm and affection to you guys today. So I'm Mark. I work for Altera. I've been at Altera since 2011. I've done various roles. And we're here today with some of the Arrow guys. Are any of the Arrow guys in the room? No, they didn't even turn up, honestly. So, we're downstairs on the Arrow stand. If you want to come and have a chat afterwards, we're just down bottom of the stairs, just over there. Right, so today, what we're going to talk about. We'll talk about FPGAs. What are they? Why are they cool things? Why are they useful? And then how do you go about using them? We'll try and squish it all into 25 minutes. And then if anybody has any questions, please just interrupt as we go along. Only if they're good questions, though. Right, what's an FPGA? And I stuck a couple of things up here. So, these are typically what they look like, a semiconductor, like you would see from anything else. It looks pretty much the same thing. You can see our various branding iterations we've been through. Altera originally, Intel, and now we're back to Altera again. And if you want to talk about that, we'll cover that later on as well. All right, what's an FPGA? So it is a field programmable gate array. So basically, it's a piece of flexible hardware you can create your own algorithms implementation out of. It's built up in a certain way, so gates being the kind of lowest level building blocks you use. These are then created together in an array to create some sort of function, some logic function you want to implement, and then they're all connected together inside the device. We're starting quite low level, quite simple here. So, as I said, made up of simple building blocks like this, and often you'll see, if you look in a floor plan of an FPGA, you'll see it's done in a kind of grid-like structure. So you'll see a kind of matrix of functions built up, and they're all doing different things. Building blocks with there'll be a bunch of connectivity between all these different blocks, and you can configure how that's connected up. So you choose the building blocks you want to build. You configure those building blocks, and then via your coding style, you connect them up. And this is all kind of handled for you by the tools. So what do these building blocks look like? This is quite generic, and I've kept the first part of the presentation quite generic. So if you look at our FPGAs or our friends at Xilinx or Lattice or Microchip or FNX or whatever, there's a lot of commonality. There's a lot of differences under the hood, but essentially you start with basically three basic primitives. So the first one is a lookup table, which you can create some sort of Boolean logic function. If you recall back to your engineering days, a bit of a Boolean logic function. They come in different flavors, maybe 4, 6, 8 inputs to them, but they're all roughly the same kind of thing. You also then get a register, a flip-flop with that, and then some multiplexers. And some of our devices have maybe 2 or 3 registers built around this. So that's the basic building block of an FPGA. The second basic building block is memory. So for us, we have small memories, 640 bits, placed around this matrix in the device, or larger memories on newer devices are all 20 kbytes each. So there'll be memory of some sort as well. So we've got the lookup table, the registers, memory, and then the other common primitive is DSP blocks. So you'll see those peppered throughout the whole device in various ways. Often in a column, there'll be repeating columns of DSP blocks. Usually they're built around like a multiply accumulate, so some sort of multiply, some adder, maybe another register as well. And these all come in different flavors. So some will have a couple of multipliers or a whole sea of gates in different ways for doing different functions. And then basically you connect these up with custom routing to create the function you need. And we'll talk a bit more about that later on. And the basic way of doing that for most people, and there are other routes into it, but most people will create some kind of code, high-level description, be it Verilog, VHDL, typically VHDL in the UK, but most of the IP blocks tend to be written in Verilog. I don't like Verilog personally, but VHDL is the king's language, I think, for this sort of stuff. It's very typed, and if you're not familiar with it, it's a very structured language, and if you're implementing FPGAs, you have to kind of think a bit about the hardware. You're not just running a bit of software, you're thinking about, okay, I write this code, and it's going to turn out a bit like this in the device. There'll be some registers here, there might be a DSP block here, there's a bit of memory. So you're always cognizant of the hardware underneath as you write the code, and VHDL really kind of helps guide you. Whereas Verilog is a bit more like C. You can write quite loose code. You can have, it's quite hard to follow sometimes, whereas VHDL can be very prescriptive. So I use VHDL, but it's kind of up to you. So people will write their code, goes through the tool. For us, it's Quartus, but Xilinx have their own tool. Everyone has their own different tool. And then that will generate some programming file for the FPGA. We've talked a bit about the hardware, but actually probably 70% of the secret sauce is in the tool, which is why entry into the FPGA world is quite hard, because the complexity in the tool has been built over many, many years. Most of us have been around for a very long time, and it's taken 20, 30, 40 years to really get to the point where actually the tool is very good, because it's very complicated. And then just quickly, why is it not a processor? People say, well, is it just like a processor? Well, not really. So typically a processor will have a fixed function, a fixed set of hardware, of an ALU, some memory architecture, some interrupt handling, address and data for memory. Generally, it's fixed function hardware that you write some C code or whatever for, and it will go through sequentially through your C code. The FPGA structure is really completely customizable. So for most people, it's the parallel function. So you can parallelize operations to all happen at exactly the same time on each clock cycle. So you can create massively parallel functions which run very fast and in a very deterministic way. So there's some kind of similarities in the way you write the code, in the way you kind of got the compilation and the bit stream flow, but underneath, it's completely different. Right, so why are we going to bother with an FPGA? Who cares? And honestly, it's not for everyone. So I think it's not a panacea for every kind of hardware project. I think you have to want to use an FPGA because there's quite a steep learning curve. The tools are complicated, although we've tried to make it easy, but it is hard. There's a lot of things to think about. But for the curious, and once you get into it, it's difficult to leave it. It's a fascinating world. So why would you use an FPGA? Well, the first thing is that they are super configurable. So you're going to create a piece of custom hardware effectively for your exact application. Whatever you need to do, you're not going to be wasting resource or power. You're going to create exactly what you need for your function. Fixed latency. We've got plenty of customers who have a deterministic latency, say between the input and the output. They need it's going to be always 25 nanoseconds, always. So FPGA will give you the exact fixed latency you need. You control exactly the delays between the registers and the timing to give you a fixed latency. Interfacing, this is the other key use case for FPGAs. Say you want 26 UARTs and you want to interface to a new weird camera from Sony and you want to have a 100 gigabit Ethernet interface. Well, you can't buy a bit of silicon off the shelf that will do all that. It's not possible. So most of our customers will use this where they've got some strange interfacing requirements which are not standard. We've talked about the reprogrammability. FPGAs, you can kind of obviously recreate your code and recreate a new thing. You can update them in the field, and also you can update just a portion of it as well. So we have some customers who have, say, the periphery of their function fixed, and then they update the algorithms remotely to do a different thing. So you can update the features as you go along in the field. Longevity is the other key one as well. We've got customers still buying parts we shipped 30 years ago. So, and we're all the FPGA guys are the same thing. Particularly in the industrial segment in places like Germany, where they're doing a lot of drive and PLC work. They ship those products for 30, 40 years, and they have to have the same parts shipping. So this is a key thing for us, and all the new families are up to 2035, 2040. So beyond my retirement age when I won't care anymore, but these kind of things are shipped for a long time. And the other key thing here is offload. We see a lot of people say, like with a PCIe plug-in card, they've got a CPU host in a system, and then they'll have an FPGA plug-in card to do algorithmic offload acceleration to as well. So that is the main reason most people use an FPGA, I would say, the main reasons. And if we look at like specific application areas, machine vision, this is kind of like I think this is a UK success story. There's a lot of companies in the UK doing vision applications for industrial applications. Loads of customers in the UK, and it's a big success story we don't talk about. So FPGA is a great fit here. So things like frame grabbers, where you're taking in super high-speed video, perhaps doing some processing and storing it. FPGA is a great fit here. Maybe you're using coax express 2 or 100 gigabit Ethernet. You're going to perhaps plug that into a PC or a host PC with PCIe connectivity. Typical, this would be a high-end FPGA function. You know, you're looking at like our Agilex 7 range or Stratix 10 range, the top end of the FPGA family. And then for things like area scan cameras, where you're looking at maybe 400 frames a second, 25 megapixel, using SLVSEC or SLVS, and outputting coax express or 100 gigabit Ethernet as well. And then right down the different flavors, right down to the kind of the lowest, cheapest camera, effectively. So there's an FPGA fit for all that. Again, mainly because of the interfacing. People have got slightly weird interfacing requirements for each application. They're trying to do a lot of processing. They don't want to burn a lot of power either. So they've got an exact function for their kind of machine vision application here. Robotics is another kind of growing application, I guess, for FPGA. And there is a show in October in London. So we're trying, actually, for this time this year, we do an FPGA show. They're everywhere around Europe. We haven't got one in the UK. So with Adam Taylor, we're going to, it's called FPGA Horizons. It's going to be in October. It's going to be quite a generic FPGA show. So all of the vendors will be there doing, you know, telling what they're talking about. And one of our guys is going to talk a bit about the stuff we're doing in robotics. So we've done quite a lot of stuff with companies like Boston Dynamics on some of their robotics applications. And this is a really nice fit for FPGA for multiple reasons, but often if you've got a multiple axis drive like this, with the FPGA, you can have a very fast control loop, nice and deterministic. You always know how fast it's going to be, how long it's going to take to do the loop, and it's quite fast as well. So you can run it, you know, 100 kilohertz, 200 kilohertz loop control, which is far faster than you can get from the standard bit of silicon. And also then if you want to add on an additional axis, well, you can just stick it down. It's very easy to do, add on another axis. And we support things like the robot operating system as well, running on some of the devices with ARM processors in them. We'll talk a bit about that later. You can run, you know, the whole robot stack inside that, and things like timing synchronization with TSN as well, which is becoming more important. Broadcast, that is another UK success story. Loads of companies doing cool stuff in the broadcast space in the UK. Studio work, so cameras, a lot of FPGAs in studio cameras. All the kind of routing matrix stuff, all FPGA based. AV/IVOP, all support for this kind of connectivity, all FPGA based. If you look at the Pro AV space, big video walls, all FPGA based. We've got a customer in the UK doing amazing high quality video walls they use for the film industry. So rather than green screening, they could use this amazing video wall behind, which looks like they're there in the room. So loads of this going on in the UK, super cool stuff. Again, all supported with FPGA, so all the video connectivity you need, like HDMI or DisplayPort, for example, MIPI, video over IP, so this SMPTE 2110 is becoming quite popular as well. Video compression as well, so H.264, 265. Loads of IP. If you're interested, we've got a nice camera demo downstairs on the stand, a 4K camera demo using our IP suite we've got available. Lots of IP for, you know, color correction, balancing, debayering, all this kind of stuff. And we are starting to see, I didn't want to talk about AI because everyone's, ooh, but there is a growing use of kind of AI in FPGA, particularly in the video and vision space, where you're looking at kind of object detection or recognizing features in a video stream. You know, the AI stuff is actually becoming more popular now in the FPGA. Yes?
What is it you think makes FPGA so prevalent in your broadcast and professional video compared to using like custom silicon?
I think a lot of that, thank you, George. A lot of that is down to interfacing, because a lot of the customers have got like, well, we need like 26 AV over IP connections, or we need gigabit Ethernet for this, we need support for this SDI camera, we need that, and you cannot buy something like that. So you have to, FPGA is mainly the reason for that, the interfacing functions. And that's supported on all our FPGAs from the high end, mid-range, and down to the low end as well. So, and not just us as well, all the guys will be doing work in this space. Another segment, how are we doing for time? Yes, okay. Military space, okay, good and bad, but politics aside on this, there's a lot of this done in the UK, and there's an awful lot of very interesting design work done in the whole application space in the military space in the UK. Huge export earner for the UK. Not all of it aggressive stuff. There's a lot of passive stuff like radar and EW work as well. Head-up displays in planes, things like that. All FPGA driven. Secure comms, so man-pat radios particularly, and they like to use FPGAs because it's not a standard product, so you can create something that's unique, then it becomes hard to hack or listen into because it's a unique design. You're not using off-the-shelf stuff. And also FPGAs have got a lot of security functionality into it, so we have features where you can effectively remotely kill the device, you can completely wipe it remotely and destroy every aspect of the configuration or the programming that was in the FPGA. You can destroy it forever remotely. So there's a lot of high security features in here which the military segment like. Comms, massive FPGA space, particularly in the radio segment. Again, another great story in the UK. Well, there used to be. I mean, back in the day when I started, there was all the big companies. We had Motorola here, Alcatel-Lucent, Nortel Networks. All the guys were doing radio product here in the UK. A lot of that has gone elsewhere, but it's still FPGA based. If you look at a Radiohead product on a pole for 5G connectivity, all of that will be FPGA based. It's got a really nice fit. We have a lot of IP available in the FPGA space, like CIPRI. A lot of the digital predistortion, crest factor reduction stuff, all the IPs available in the FPGA space. So huge radio space. Not quite so much in the core network. I think a lot of this tends to be kind of CPU style now. And all the 6G stuff will also now be done on FPGA as well. If you look at like guys like Ericsson, for example, they're developing the new 6G stuff. That's all be FPGA based as well. Data center is not something I know much about, but we're seeing, I think, more FPGA appearing in the data center, mainly because people are starting to get a bit freaked out by the power requirements. You see, like the power consumption of ChatGPT, for example. How do we reduce that a little bit? And GPUs, whilst they are amazing at what they do burn through a lot of power. It is a general piece of silicon. Whereas an FPGA, you can say, well, I'm going to create exactly the function I need, increase the performance, and reduce the power in the data center. So we see, particularly in things like genomics as well, gene sequencing, we're seeing a lot of FPGA use as well, because that's quite process and power intensive. Network attached storage as well. RAID drives connected into the network. FPGA will sit in the middle of that and orchestrate the data flows. So we're seeing a lot more of this kind of in the data center as well. And also around security as well, like securing links between data centers, 100 gig, 400 gigabit Ethernet hops between data center nodes. A lot of the guys are looking to secure those now with things like MACsec and IPsec. Often that will be done in the FPGA as well. Right, so that's why FPGAs are cool. How do we do FPGA? What do we do? So a brief product pitch. So we've been around forever, 40 plus years now, and we've just been spun out from Intel again. So we were acquired by Intel in 2015. We're now a separate company, which is roughly 50% owned by Intel. So we are now in charge of our own destiny going forward. And so we're almost like a 40-year-old startup now. A lot of the people who've been around a long time are quite excited. There's a new energy about the company. We're kind of freed from the shackles a little bit, and we can go on and do our own thing. So it's quite an exciting time for us. Lots of stuff going on, lots of smart people. Just want to cover the portfolio briefly, because actually, although it is focused on us, it gives you a flavor. If you're looking at FPGA, if you go and say, talk to the AMD guys, they will have a similar kind of lineup of products. The Lattice guys also the same kind of thing. So you'll often see a power and cost optimized portfolio. So for us, that's the Max and Cyclone family have been around forever. And then this year, we've got a new Agilex 3, which is a new family coming out next month. So if you're looking at a very small, cost-efficient, power-optimized architecture, you'll have a part for that. Mid-range devices, Agilex 5, if you look down on the stand, on the arrow stand, there's the 4K camera demo down there, running 4K 60 with some video pipeline edge inferencing running on Agilex 5. That's out now. And then you step into the kind of expensive area, the high-end, really super capable devices and things like Agilex 9, which has got 64 gigabit ADC and DAC in it, but you'll be paying around about $20,000 per device for some of those. So it's a little bit niche. It's EW radar kind of application. And then we'll have a full, everyone has tool flow. So our tool flow is called Tortoise. We've got a bunch of IP. We'll talk a bit about some of the embedded processor applications. And then there's high-level tool flows as well. We do, okay. So the embedded stuff. People say, well, what do we do this for? So we've had soft-core processors around forever. We used to have a processor called Neos 2, which is a MIPS32-based architecture. And you could have a really tiny little core, so basically like a basic MPU. You could write a bit of bare metal C on, and you could run some control application on it, and it would embed in the FPGA itself. We've now got Neos 5. Everyone's gone RISC-V, so this is our new RISC-V family. And you can have, again, quite a small core, all up to something that will run Linux on it as well. So you want to run a kind of a Linux stack, you can run that on Neos 5. I think in 2012, 13, we did the first embedding of ARM. So it was the time that we'll take the ARM cores off the board, we'll put ARM cores into the FPGA as hardened bits of silicon, because, hey, why not? We'll have a bit more of the pie. So everyone was doing this, us and Xilinx and everyone else was doing this. We started off with A9 processors. We've got A53s, A55s, and A76s in the latest family. So you'll see quite a lot of ARM processors, and all the guys will have ARM cores inside their FPGAs, because a lot of people use them for often just running Linux, for example, on their, you've got a Linux application class processor running Linux there on the FPGA. You can use it kind of for lots of stuff, even if it's just board management or little bits of twiddling around the edges. It's quite an easy way of getting a processor up and running. And then tool flows. So we did an analysis of this. I think about 97% of people still write RTL. So they still write VHDL or Verilog for their FPGA flow. So most people do that. And you always have to do some of it. You can never really get away from that. If you're an algorithm developer, you can start to step into some of the high-level flows, but most people will end up doing some kind of RTL input into the tool. We've got a high-level IP tool, so you can stitch together. So say you're putting together a system with an ARM core in it. The high-level tool will say you can just basically drop these bits of IP in, like here's an ARM core, here's some memory, here's an interface to something else, and you can connect it up graphically and let the tool worry about the code underneath it all. So all the guys will have some form of high-level tool flow. And there's a bunch of then debug tools as well, things like logic analyzers built into the tool that you can then get traces out of the fabric onto an external system, either streaming it or frame by frame. So there's lots of debug tools available. For embedded developers, we generally see most people split the development between hardware and software. So we'll have guys writing RTL, and then we'll have software teams who don't even know it's an FPGA. They're just using a standard kind of Eclipse-based tool to write their C code or whatever, and then it just runs on the FPGA. The FPGA guy's done the board support package and all the other stuff, and the software guys are often just effectively in ignorance of what they're running it on. They're just writing their software flow as normally. And we're using an Ashling debugger now, either for the Neos or for the ARM systems as well. And then George's favorite, AI. So we've tried to keep it quite generic, I think. Not everyone's done so. So if you are looking at some kind of edge inferencing thing, all the standard models, we can split that out. And we use the Intel OpenVINO tool as well. So you can take, say, a TensorFlow model you've got, put it through OpenVINO, it will spit out an optimized model, which then goes through our tool here to fit into the quarters flow. So effectively generating a bit of black box IP for you. So you don't need to know too much about the way the FPGA works. There's tools available if you're looking at kind of edge inferencing. And actually, it's not just edge inferencing. We've got some customers who are doing training now as well with FPGA because it's a lot more efficient power-wise. But again, it's not so easy to do as GPU, super easy to do. FPGA, you've got to really think about it. But if you need to, it's available. Yes?
Thanks.
Oh, he's got a microphone.
Yeah, I know. It's well cool.
Look at that.
Hey, you spoke about pretty much everybody's still in RTL at some point.
Yep.
What does it take to build those RTL skills in order to let's say, adopt a flow from an embedded or an algorithmic developer? I mean, what would it take one of the people in this room to get those skills?
Yeah, we talked about this yesterday, actually. We were talking about this. I mean, when I started, there was a company called Doulos that's still around, and we did a 5-day VHDL course, and it was proper intense. It was like full days, and then in the evening you did lessons for the next day. It was really long days, but you came away thinking, my God, I actually know some stuff. So there are courses available, but you don't need to do that. And I think actually, if you're looking at quite a structured language like VHDL, it's quite, once you've got the structure in place, it's actually quite easy to write code. It's quite C-like in a way of like writing a counter, for example. It's very similar. So there is a learning curve, and you have to think about the parallel structure and the custom hardware. It's not a fixed function. You're thinking about, yeah, I've got this custom hardware I've created. You know, how does my code work there? So you have to have always a mind to the hardware you're writing it. But there's plenty of training out there. YouTube videos we talked about as well. I think DigiKey have got some nice. I think there are Verilog stuff, but there's some YouTube videos out there. There's plenty of training for free, and we've got some free training stuff on our website as well. So in the interest of time, we'll skip through. Security, I think, is becoming quite important. And we've still got many people, especially with the Cyber Resiliency Act, I'm still not entirely sure what that's going to mean to most products, but I think if you have some connectivity in your product with some way of somebody being able to connect into it, whatever it is, you will have to comply to the Cyber Resiliency Act in some way and show you've done due diligence in how you're securing your design, how nobody can mess around with the design. And FPGAs are actually very well sorted here. Most of us will have some kind of security built into the device for securing the bit stream, thinking about authentication, encryption, and then through to high-level features like attestation, where you can get the FPGA to report cryptographically, securely, what it's actually running on the device. So we've kind of thought a lot about this and the security aspect, and from a supply chain point of view as well. Who knows what's going to happen with Taiwan at some point. So we've kind of, our new devices are actually all mostly coming out of the US, but there is a fab in Ireland as well that is going to be geared up for producing our devices as well, so we can produce in Europe and not just rely entirely on Taiwan, because who knows what's going on there. Interest of time, we'll skip on it. Just to say, yeah, supply longevity. Look out for this. I think everyone's doing this now, actually, but you know, if you've got a product that's going to be in the field for 10, 20 years, FPGA's what you need. I put this in, this is a screenshot of the Quartus tool, what it looks like. So if you're a kind of software developer, it probably looks similar to most IDEs. It's not, sorry, you probably can't see this very well, but you end up with like a project throw. You can set your projects, different projects, revisions of the projects. You get a file view. It can be flat or hierarchical or blocks of IP. It's all script-based, so you can run this entirely scripting. You haven't got to use the tool at all. We have plenty of customers who run like script flows, regression-based scripting outside of the tool. It supports all of that. And then you get like a compilation flow window like you would get in an IDE, you know, various steps of the compilation shown on the screen. There's you can't see it on here, don't know why, but there's another IP view as well, so you can drag and drop blocks of IP you've got into the system quite quickly. The tool flow itself, it's not so straight. So there's a few things to consider. So your design files at the top, if you've written your RTL, a bit of Verilog, for example, that will then go through analysis, elaboration, and synthesis. So basically, this is the code, the tool taking your code and saying, well, this is going to look like a lookup table and 6 registers and a bit of memory over there. So it's taking your code and translating it into the primitives on the device. Constraints, this is what everybody hates. So this is the nasty bit, honestly. You have to constrain your design. You have to give the tool some guideline and say, well, actually, I want to run my clock frequency at 600 megahertz, or I need my latency between the input and output to be this many nanoseconds. You have to set a constraint here. We use a standard format, Synopsys design constraints. It's horrible. Everyone hates it, but it's an industry standard, and you have to get used to it. So if you're going to do FPGA stuff, you need to know about SDC as well. Once you get into it, it's okay. But so you have to have that as well. That will feed into the fitter, and that then guides how it does the routing we talked about earlier. The routing is guided by how you set the constraints in the device. And then it will generate a bit stream to program the device, do some time analysis, and then you can do things like gate level simulation or functional simulation. So most people use what I would call model sim. It's now called Questa Sim, but basically it's an industry standard simulator. There's others available. you can do at the functional stage, just built on your code alone, or you can do it if you're, this is for the brave, a full gate level simulation where it's cycle accurate. It's taking the output of the tool, the full netlist of the FPGA, you can simulate at that level as well. We have some customers who have to do that for certain applications. It takes forever to run, but you can do it. So if you want to get started, look on our website. There's a load of cool resources on there. The tools for the mid-range and low-end stuff are downloadable, and it's a free license, no licensing cost at all. We've got lots of training online as well. If you want to see me, I can send you a link for all the training resources around things like VHDL, timing constraints, a favorite, lots of stuff like that. Loads of example designs available for free. Lots of nice dev kits. This is a new one from Trends as well. This is the Agilex 5 family on here. Nice little form factor, Raspberry Pi style. I think that's about $80, that board. So there's a bunch of stuff. And I've actually got a couple of dev kits if anyone wants one. Come and see us on the Arrow stand. I've got a few to give away, and I think the Arrow guys have got a couple to give away as well. Oh, look at that, on time. Apparently, I've got to show you this, and you have to scan this to get a CPD credit, whatever it is, if anyone knows what that is. Anyway, any questions? Please.
About cloud applications, like can we integrate it with AWS or like GCP or Azure? Can we use it for commercial software development and like Raspberry Pi? You mentioned like we can integrate it with cloud applications and stream our data across different sources.
Yeah, you can use. We've got I think Microsoft and AWS also use. There's FPGA as a service, so you can use. They've got a bunch of FPGA cards sat in the cloud somewhere. You can use those as a service, paid for.
Okay. But can we do that on the $80 chip that you mentioned? Like, what is the minimum cost of that FPGA that we will be able to integrate with cloud-based applications?
That I don't know. We'll talk about it on the stand. I'm not sure. I have to think about that.
No problems.
Yeah. No other questions? Oh my goodness. Okay. It's gone crazy.
So thank you very much for your presentation. My question would be does Altera support any sort of high-level synthesis tool?
Yeah, so I didn't cover that. Yes, so we do. Yes. Let's go back. So yes, people who, and we talked about this again, a few of us talked about it yesterday. We do a C to gates flow basically called one API. So basically you can write your code in C, C++, and it will generate RTL for you. It will generate a bit of Verilog or VHDL for you, but it's like a black box effectively.
Is it free to get that software?
Yeah, it's part of the tool. Yeah, absolutely. Yeah.
Okay, great.
Yes.
Thank you.
Yeah, so I didn't mention it. I totally forgot. I had it on my notes as well and everything, but I didn't even look at that.
I went Team Red like 6 years ago because of the high-level synthesis.
I will forgive you.
Thank you.
Yeah, no, we have a flow as well. So, but actually, not many people use it. I mean, it's there, but you can't do the whole thing like that. You know, you have to have an awareness of your PCI interface or you're interfacing elsewhere. You have to have somebody's going to have to do that awareness of the hardware for you. But yeah, for black box IP, yeah, it's nice. C to gates flow is good.